Hello and welcome back to another LeetCode problem. So we're going to be doing problem number 120, triangle. And it's a pretty interesting dynamic programming problem, but we're going to try to make it even more efficient. So let's read it. Given a triangle array, return the minimum path sum from top to bottom. For each step, you may move to an adjacent number of the row below. More formally, if you're on index I, you may move to either I or I plus 1. And so what this is going to look like is, let's draw this example. So we have 2 34s are triangle. And then we have 6, 5, 7, 4, 1, 8, 3. And so the way this works is we start at the root, and then we can either move left or right. At least the way I drew it here. So what's the minimum path here? Well, I think it's actually going to be this one right here, right? So 2 to 3 to 5 to 1. And that's going to be path sum of 11. But we can go other ways, right? And so let's try to figure out a recurrence relation and like where we could go. So at every single node, we can either go here or here. And at this node, we can go here or here and so on. And so it's pretty easy to find a recurrence relation where we can just figure out like, okay, at like the sum from a node, right? So let's say we're at node 3. The sum from node 3 would be max, or we're trying to minimize actually, min. Then we either go, so it'd be, we would add 3, right? Because we have that in there. Then we have min, and then we go left, or we go right. Right? That's how we're trying to minimize it, is from a node, we can go left or we can go right. And so it's pretty easy to see, like just really quickly, how you would draw a dynamic programming solution here. You would just have a dynamic programming, right, of some index. So let's just call it like row column. And then you pretty much just say, return whatever the value is. So let's just say our array is like, let's write this out. So let's say our array is like R here. It would be like R row column plus min dp of, like, I think you can either go like one column down or one column to the right or something. But anyway, it would be like, dp of whichever two places you can go, right? Something like that. Right, so you can either go left or right, and so yeah, so it's the same index or the index plus 1, I believe is what they said in the problem. Yeah, so we can either move to index I or I plus 1, and that's kind of like how we could do a simple memoization DP problem here. And then all we have to do is we would just have to save these states. So I'm not going to code that up, but I think this is simple enough to where you should be able to do it, where you only have, you could just go down 2 different ways, and then you keep track of the sum, and then your base case can be once you can't go down anymore, right? So you're like, you're out of bounds. So you keep going down, out of bounds, return 0, and then you just go back and add that up. And then we can also have a visited hash map. But the problem is, so we're actually going to focus on the follow-up for this problem, because this is like a better solution. So we're going to do that. For a lot of problems, I don't do bottom-up. For this one, I decided to do bottom-up because you're actually getting a better solution. So they're asking, can you do it in big O of n extra space, where n is the total number of rows? And what we're actually going to do here is we're technically not even going to use big O of n extra space. We're just going to figure out how to override the input to get our solution. Okay, so I'm going to redraw the triangle again, and we're going to look at this. So we have a 2, we have a 3, we have a 4, 6, 5, 7, 4, 1, 8, 3, right? Okay. So we're actually going to figure out how to override their input. So remember, from each node, we can either go left or we can go right. Now let's think about it another way. Let's think about, from each node, how can we get to that node? So from each node, we can either go left or right. That means from each lower node, we can either come from the left node or the right node, right? So from like obviously for these nodes, you can only go to them from one direction, right? But so like these would all be like this. But let's say you're at node number 5. How can you get to node number 5? Well, you can either come from here or you can come from here. Then if you're at node number 1, how can you come from this or this? 8, this to this. So you can see how these are connected, right? So like the way to get 8, the way to get down to 8 was you'd have to be at 5 or 7. And so we're going to use that to override. So I'm actually going to draw on the right like how we're going to override the outputs. So we're actually going to start at this node here, and then we're going to go all the way down to this bottom row. And so the way that's going to look is we start at this node here, so we can't like, and then we're going to, the way we're going to do it is for this initial node, we're just going to have it have its value because for a sum, we're starting here. But then when we get down to these other nodes, it's pretty straightforward. So for nodes with one parent, the sum, like up to this situation, is just going to be the value of the node plus the value of the node above, right? So for like this node, the sum to get to here would just be 5. 2 plus 3, because you can only get there in one way. 6 here. Now we have 3, so I'm actually going to draw it like this. We have 3 more nodes here. And now for this left node, we can only get here one way, right? So for this left node, it's just going to be 5 plus 6. So if this is 5, you can only get here one way. So it's just going to be 5 plus 6, which is 11. And then for this node, you can also get here one way, as you can see with this line. So that's going to be 6 plus 7, which is 13. But now for this node, we can actually come here one of 2 ways. But it's really straightforward how we can get the sum. Because we can come here one of 2 ways, we're just going to be greedy and pick the minimum sum. It's not really greedy, but we're just going to pick, because we can only come here in 2 ways, we're just going to take the minimum sum. So like, if we can come here, if this 5 is smaller, then we'd want to take this path to this node every time, right? And that makes sense, as you can see. Like, we'd rather take, so this node is actually this one, I believe. So how would you rather come here? Would you rather come this way or the right way? Well, obviously you'd rather come the left way. And so because we are going to be storing these sums, we can just figure out, like, for a node with 2 parents, we can just take the smaller sum. So we can take the 5 here, and then the value of this node is a 5, so this is going to be 10. Okay, now we have 4 more nodes, so we have a node here. There's only one way to come here, though. It has a value of 4, so it's going to be 15. And then there is a node here, a node here, and a node here. And these lines look like this. Okay, so this node on the right, there's only one way to come here, so it's going to be 16. Okay, now these 2 nodes, we're going to take, remember, we're going to take the minimum sum, because we want to like be kind of greedy and just always take the smallest sum. And so this is going to be 10 plus the node is 8, so that's going to be 18. And then this is going to be, we want to take 10, and the node here is 1, so that's going to be 11. And then we can just take the smallest sum. So did we get the right number? Yeah, we did. So once we fill out the bottom row, like once we're out of bounds, we can stop, and then we just look for the smallest sum in the bottom row, right? Actually, yeah, we look for the smallest sum in the bottom row because we have to get a sum from top to bottom. So the output has to be in one of these bottom rows. And so now we are just going to be overriding the input here. So we're actually going to be using big O of 1. And time-wise, it'll be the same. It'll still be n squared, because the way it works is it's technically an n by n matrix, even though it's not. And for big O, I think this ends up being like n squared over 2 or something nodes. But, you know, for big O, we don't care about the constant value, so it's technically going to be n squared runtime. Okay. And so let's focus on coding that up. So what we need to do is we need to traverse every single row, and then we need to traverse every single row starting from the second row, technically, because the first row is going to be, like in our picture, the first row is going to be like, it's not going to have a sum, it's already going to have a value. Okay, so let's do that. So that's going to be what? For I in range. Do we want rows and columns here or something? I don't think so. Yeah, I don't think we need it. Okay, so length. So this is going to be triangle. And then we are going to actually... Actually, let's get the rows, might as well, right? So rows. We can even do columns, I think. Or no, let's just do rows. So rows equals length triangle. Okay. So remember, we're going to start at row 1. And this is going to be rows. Now we need to traverse every single index in that row. And they're going to be different, right? So they're going to be like, some of them will have 2, some of them will have 3, and so on. So we need to traverse, and then we need to figure out, is the index above it valid? And is it always going to be? Not always. Yeah, okay. Okay. So really what we want to do is, and I think this is the better way, is for these outside nodes, we want to like how do we want to do this? Yeah, I think what we're going to do is for these outside nodes, we know that like there is no right node here, so we don't have to check for that. So if the node is an outside node, which means, let's just think of the index here. So this is row 0, column 0. This is like the Pascal's triangle. This is row 1, column 0, and so on. This is row 1, column 1, row 2, column 2, row 2, or 3, column 3, and so on. So what we're actually going to do is use this. So we're going to say, yeah, so we are actually going to take the first and last element in the row and then manually like get those, and then we're going to do the rest. So we're going to say triangle I 0 equals triangle I minus 1, right? Previous row 0, because like as we go down this left side, the node is just the sum of the previous node and itself, and this previous node is going to be column 0 and the row before, right? So if this is row I, this is row I minus 1. Okay, so that's going to be that plus, so I guess we could technically just do this. Okay, so that's the first row. Now we also need the last row, or sorry, not the first row, that's the first column. Now we are also going to use the last column here. So triangle, and this is going to be I minus 1. And so if you think about it, the right side is the same thing. So the last thing in the row is just going to be the sum of itself plus the last thing in the row before that. So this literally should be the same thing. Triangle. Yeah. And so this is going to be I minus 1. Yeah, same thing. Okay. So now that we have those, now we need the middle ones, right? So we did like these, and we need the middle, whatever's in the middle. And so what's the indices of that going to be? Well, it's going to be 4j in range. So we're going to start at 1. Then we are going to go to length of what? Triangle. And then this is going to be the current row we're at. So triangle I. But remember, we don't want the last element, so I think we need to do this. There we go. So now all of these elements should have 2 parents. Because, for example, like for this element, this would be row 2, column 1. Yeah. Row 2, column 1, row 3, column 1, or 3, column 2, and so on. Yeah, okay. I think we're good here. We'll test it out, but I think we're good. Okay, so this is going to be, now that we actually got which ones we need, it's going to be pretty straightforward. So it's going to be triangle ij, and same thing, plus equals. Now we need to get the minimum of triangle, and then this is I minus 1. And so remember, we got here from which nodes, right? So like, let's say we're at this node. Let's redraw this. There's so many. Okay, so it's like 2, 3, 4. And then we have 6, 5, 7. Actually, hold on. Let me just get rid of all this and redraw it cleaner. Okay. So 2, 3, 4, 6, 5, 7, 4, 1, 8. Let's draw like this. Okay, so let's say we're at this node. What are the actual parents, right? So this is at column index 1. So the parents are at column index 0 and column index 1. So it's going to be column, the same column, and then it's also going to be column minus 1. So previous row, column minus 1, and column, let's test that just to double check. Let's check for this 8. So this 8 is at column 2. This 5 is at column 1, column 2, right? So you could see, like, yeah, if this is at column 2, then the two parents are at column minus 1 in that column. So that's what we're going to use, and they're both at row minus 1. So row minus 1 this, and then row minus 1 this for the other one. Yeah, so this is the two parents. This is parent 1, parent 2. Okay, so that helped to visualize that. So it's going to be j minus 1 and triangle of same thing, row minus 1. I guess what I should have probably done, that I'm not going to fix now, but what I could have probably done to make this a lot cleaner is imagine I is row and j is column. Then it would be, whatever. We'll just change it. Might as well. Then it's going to make, like, it's going to be more legible instead of these i's and j's. So. Okay, and this is column. Hopefully that is easier to read now for you. So triangle, row minus 1, and column. And that should be it. Okay, so now we just need to simply return the minimum of the bottom row. So that's going to be triangle minus 1. And that should be an array, and we just return the minimum there. See what happens. Say it ain't so. It is so. Nice. Okay. So yeah, so it's pretty straightforward. Once you kind of realize the trick that you can just, instead of doing a DP, you can actually just go bottom up, and then we know that, like, how we can, once we draw these paths that I drew with the arrows, now that we know how we can get to every single node, we can easily figure out where we'd want to come to that node from. It's pretty straightforward with the bottom up instead of top down. So I just wanted to show that, because usually for most problems for memorization and for bottom up, you're going to have the same time and space complexity, but in this one, that's not the case. Okay, so let's do the time and space here. So for the time, like I said, it's going to be n squared, because for big O, you think worst case. So this bottom row is going to be length n, so it's n times n. So even though these are a little bit shorter, it's technically not n squared. It's going to round up to n squared. So for the space, this would be big O1. Because we didn't actually make anything else, we're just overwriting an input here. So we didn't need to make any extra space. And so that's going to be big O1. Okay, and that's all for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching. Bye.